All right, welcome back to our week 2 recitation video. So this week we will be focusing on the topic of metric spaces. So in topological data analysis, the most common approach in practice is that we have some data set which we want to perform, our methods of topological data analysis on, and this data set initially is just a collection of points. Well, a collection of points on its own, we can't really use methods of TDA on it, so we need to convert it to some other type of object. And one of the most common standard approaches is to convert this collection of points to what's called a metric space. So what's the definition of a metric space? Metric space is a pair x comma dx, where x is a set of points, and dx is a function from x cross x to the reals, satisfying the following three properties. So first, we must have that dx between x and y equals 0 if and only if x equals y. So this is saying that the distance between 2 points is equal to 0 if and only if those 2 points were really the same point. The second property states that dx between x and y equals dx between y and x. So the distance between x and y is the same as the distance between y and x. This is called the symmetry property. And last but not least, the third property states that for all x, y, and z points in our metric space X, the distance between X and Z is less than or equal to the distance between X and Y plus the distance between Y and Z. And this is known as the triangle inequality. And for notation, if the set X is understood, we often write just D without the subscript X for the metric. And yes, we call the function d from x cross x to the reals a metric, and also we call it a distance. These words generally are used fairly interchangeably. So what we can think of pictorially is a metric space. We have just some set x, which is a collection of points. And then we have a function d such that whenever we pick 2 points, little x over here and y over here, d will give us a notion of distance between these 2 points. One very important property of metric spaces is the following fact. Which is that for all x and y in the metric space X, the distance between x and y is greater than or equal to 0. In fact, I've seen some places before where this property was stated as a condition that metric space must satisfy in the definition of a metric space. However, stating this condition in the definition of a metric space is redundant because here we're claiming that it follows from properties 1 through 3 already listed. So we'll prove this. If you want to try that out on your own, you can pause the video for a couple seconds and try to prove that this follows from 1 through 3. All right, so whether you've tried it or not, if you were able to prove this, then good work. Otherwise, we will continue with the proof here. So first, we write for all x and y in X, note that the triangle inequality implies the distance between x and y plus the distance between y and x is greater than or equal to so this is by property 3, triangle inequality, the distance between x and x. And by property 1, this equals 0. By property 2, the left-hand side of this inequality equals twice the distance between x and y, because the distance between y and x equals the distance between x and y. So combining this, we get 2 dxy is greater than or equal to 0, and we divide both sides by 2, and we get the claim. So this is a very, very important property of metric spaces, that the distance between any 2 points is non-negative. Let's go through some examples quickly. So probably the first example of a distance that you learn in elementary school, even if it's not phrased as a distance at that point, is where our set x is all real numbers, and the distance between a point x and y, so between 2 real numbers x and y, is the absolute value of their difference. The claim is that this is a metric, and the proof is fairly straightforward. So to check condition 1, the absolute value of x minus y is 0, if and only if x minus y is 0, if and only if x equals y. Similarly, the absolute value of x minus y equals the absolute value of y minus x. That's fairly immediate. The triangle inequality is the only condition which requires a little bit of work, and it really follows from this inequality on real numbers right here, which is something quick that you can prove in a couple lines, but I'll leave that as an exercise. And if we assume knowledge of this inequality, then for all x, y, and z in the real numbers, the distance between x and z equals the absolute value of x minus c, which equals the absolute value of now x minus y in one parenthesis, and then plus y minus z in another parenthesis. So this is a standard approach, I would say, when we're trying to prove triangle inequality in some general settings, is to take x minus z, or the distance between x and z generally, if we have a form like this, and in the middle, include a minus y and a plus y. Then from this basic fact with real numbers, we break up our one absolute value into 2 absolute values. And from there, by definition, this is the distance between x and y plus the distance between y and z. So this is a very, very standard metric that, again, you learn very early on in life, if not phrased in this way. And it's simply, we have a real number line, and we have some value x and some value y, and this length here is the distance between x and y. So very elementary example here. This is a special case of a more broad class of metric spaces, which is very core to really just study of metric spaces in general, which is actually a family of metric spaces, being the Minkowski distances on Euclidean space. So this family of metrics is defined as follows. So it's going to be a metric on n-dimensional Euclidean space. For a point x in Rn, we write it out coordinate-wise with coordinates x1 through xn, where each coordinate x sub I is a real number. The family of Minkowski distances is defined for based on a constant p, where p ranges from 1 to infinity, and we define the distance function dp from Rn cross Rn to the reals as follows. So the distance dp between x and y, points in Rn, is the sum from I equals 1 to n of the absolute value of xi minus yi raised to the p power, and then all raised to the 1 over p power. So some common examples here. The first one is that if the case is that p equals 2, then this is the classic Euclidean distance. Recall, I think this is something learned in middle or high school geometry. If you have 2 points x1, y1, and x2, y2, and look at the distance formula given above for Minkowski distance with p equals 2, we would have d2 of x comma y is the absolute value of x1 minus x2 quantity squared plus the absolute value of y1 minus y2 quantity squared, all raised to the 1/2, which equals the square root of x1 minus x2 squared plus y1 minus y2 quantity squared, which is the normal formula that most people have memorized for Euclidean distance between points in the plane. Another example, if p equals 1, then the 1 Minkowski distance is just the sum across all coordinates of the absolute value of the difference in the coordinate. So what we did in example number 1 with distance between points on the real line, well, that's just a special case of Minkowski distance with n equals 1 and p equals 1. So as an exercise, we won't be covering this in here, but it's a good exercise to try on your own, is to prove that for any n, a natural number, and p ranging from 1 to infinity, that dp from Rn cross Rn to the real numbers is a metric. The first two conditions for metric space are pretty quick and straightforward to show. The triangle inequality definitely involves a little bit of work, but if you get stuck, then the key fact is Minkowski's inequality, which I would encourage you to look up. And you can also look up the proofs. So some of the proofs might be a little bit beyond the scope of this course. It's important general math inequality and real analysis. And the triangle inequality for Minkowski distances follows almost immediately from Minkowski's inequality. So we've discussed the case when p is greater than or equal to 1 and strictly less than infinity. Note, if we look at this definition, it wouldn't make sense to state p equals infinity in this form, because xi minus yi raised to the p power, if p is infinity, that's not mathematically well defined, and similarly raising something to the 1 over infinity power is not well defined. So we have a special definition. If p equals infinity, define d sub infinity function from Rn cross Rn to the reals as follows. So d infinity, the distance between x and y, is defined to be the maximum for 1 less than or equal to I less than or equal to n of the absolute value of xi minus yi. So it's the maximum of the difference in each coordinate. For example, if x is, say, 1, 3, 5, 7, and y is maybe 8, 6, 5, 4, then we would say d infinity xy is equal to 7, because we look at the difference in each coordinate. The difference in the first coordinate is 7, difference in the second coordinate is 3, difference in third coordinate is 0, difference in fourth coordinate is 3. So the maximum of all those distances was the distance in the first coordinate, which was 7. So we claim that d infinity is a metric. I'll maybe give you a moment to try and prove this on your own. To pause the video and do that if you would like. Otherwise, in a couple seconds, I will begin the proof. Okay, so condition 1 is very, just straightforward to show. So I won't really go into that. We have to say d infinity xy, again, equals 0, if and only if x equals y. Well, x equals y, this precisely means that x and y agree in every single coordinate. From that definition, property 1 is clearly satisfied. 2 is also clearly satisfied, just because if you swap the location of x and y inside this absolute value, it doesn't change the resulting absolute value. For condition 3, suppose x, y, and z are in Rn. And furthermore, suppose that d infinity between x and z equals xj, the absolute value of xj minus zj for some fixed 1 less than or equal to j less than or equal to n. So recall d infinity were defined as taking a maximum over all n coordinates of the absolute value of the difference in that coordinate. And we're just saying that, this distance then must be realized by some specific coordinate difference. And we're saying that that is occurring at index j. From this, we have d infinity xz equals absolute value of xj minus zj. Then from what we discussed earlier, this is less than or equal to the absolute value of xj minus yj plus the absolute value of yj minus zj. But then now we notice that these are two specific coordinate differences between the elements x and y and the elements y and z respectively. So this is less than or equal to the maximum for 1 less than or equal to I less than or equal to n of xi minus yi plus the maximum from 1 less than or equal to I less than or equal to n of yi minus zi. This element, this value must be less than or equal to this value, and this value must be less than or equal to this value, because we're just considering a particular element which is considered in a set that we're taking the maximum of. Then, by definition, this is d infinity xy plus d infinity yz. And so the triangle inequality is satisfied. So these are just some common examples of metrics which come into play in many instances, when we're taking an initial set of points and converting them to a metric space. So now I want to discuss a couple alterations to the definition of a metric space, which appear throughout topological data analysis among other fields as well. So the first is what's called a pseudometric. So in a pseudometric, the metric function still needs to obey symmetry and the triangle inequality. It also still requires that the distance between a point and itself remains 0, but we can have, in a pseudometric space, distinct points x and y with distance between x and y equal to 0. So this is a relaxation of condition 1 for a metric space. We still require distance from a point to itself is 0, but unlike a metric space, distinct points can have 0 distance. An extended metric is another type of relaxation of the metric definition. So now an extended metric is not a function from x cross x to the reals, but from x cross x to the reals union a point at infinity. So symmetry holds the same as with a normal metric. Condition 1 also holds the same as with a normal metric. But now that we have the distance between two distinct points can be infinity, we need to make some conventions for the triangle inequality. So the triangle inequality still holds, but we need the following pieces of logic. We say infinity is less than or equal to infinity. We say infinity plus infinity equals infinity. And for any constant value, c and r, we say that c is less than or equal to, and specifically, we can just say strictly less than infinity. And that c, any constant value plus infinity equals infinity. So with this new logic on sort of infinite arithmetic and infinite inequalities, everything holds, all the properties hold the same as for a normal metric space. The last type of alteration to metric definition that I want to state, which is closely tied to the notions of clustering you discussed in lecture, is that of an ultrametric. So both pseudometric and extended metric were relaxations of the definition of metric. Namely, what that means is every metric space is also a pseudometric space, and every metric space is also an extended metric space. But on the flip side, an ultrametric space is a strengthening of the metric space definition. So what that means is it does not hold that every metric space is an ultrametric space, but instead it's the reverse. Every ultrametric space is a metric space. So in an ultrametric space, conditions 1 and 2 for metric space in the metric space definition are satisfied, but the triangle inequality is replaced by the following inequality. So we say that for all x, y, and z points in our space X, the distance between X and Z must be less than or equal to, now not the sum between the distance between X and Y and the distance between Y and Z, but now the maximum between the distance from X to Y and the distance from Y to Z. And this is known as the strong triangle inequality. Okay. So these are just 3 other common alterations to the definition of a metric space, which we'll see throughout this course. In particular, two of the most commonly used metrics in topological data analysis, which won't discuss, give any definitions for today, but they're known as the bottleneck distance and the interleaving distance. Those will be defined later on in this course. They are extended pseudometrics on collection of persistence modules. So what this means from the above definition is that bottleneck distance, interleaving distance, both of these distances can be zero on objects which are distinct, and they allow distinct objects to have infinite distance between each other, but they still satisfy the triangle inequality as well as symmetry, and that the distance from an object to itself is zero. So they are extended pseudometrics. So this was a quick primer on some of the theory of metric spaces. And in the other video for week 2, we will discuss some very concrete ways in which a data set is viewed as a metric space, as well as look at some code in MATLAB, which helps us to convert a collection of points to metric spaces. So look for that in that video.